Good morning, everyone. My name is Tianrou from Penn State University. Today, I will present our work, DEEPTYPE, refining indirect call targets with strong multi-layer type analysis. Indirect calls are commonly used in C, C++ programs, such as Firefox, Chrome, LibreOffice, Apache HTTP server, and many other applications we use daily. Determining the target of an indirect call is non-trivial, considering the wide use of indirect calls and its importance in program analysis and security analysis. There are many existing approaches to indirect call target identification. Database analysis tracks data flow to precisely determine where a function pointer points to. But it is time-consuming. For example, using SVF to analyze Linux kernel could cost several hours to days. Type-based analysis is more efficient. It checks function signatures to find matched functions for indirect calls. But it can have high false positive rate, especially for large programs where many functions share the same function signature. Then, multi-layer type analysis, MLTA, was proposed. It is an improved type-based analysis, leveraging extra type information from composite data structures. For example, this function pointer, B right arrow, A right arrow PTR, has multi-layer type void int star, struct A, struct B. MLTA checks if the multi-layer types of functions and indirect calls match to identify targets. However, multi-layer types bring challenges in type matching. There are two forms of information flow that affect multi-layer type matching. The first one is type transformation. Here, WOP is assigned to U right arrow UW. In this program, we can see these two functions involving WOP respectively hold the address of these two functions. Due to the information flow from type transformation, these two functions can propagate to another two function pointers that involve U right arrow UW. This is first kind of type information flow. The second form is parameter passing. Here, the actual parameter is passed to the callee function at line 13, and the corresponding formal parameter is iCallPTR. It has different multi-layer type with the actual parameter. And this kind of information flow can also cause function propagation. Thus, the indirect call at line 15 has target right to protected mem. The indirect call at line 28 has target right to shared mem. However, if we cannot correctly address the information flow in this program, we can see these two indirect calls multi-layer types do not match with these two functions indirect calls, leading to missing targets, which indicates unsoundness. To address the challenges, MLTA splits multi-layer types, simplifying multi-layer type matching to traditional type matching. It records mappings between split types and associated functions, just as this table shows. The splitting operation can weaken the restrictions provided by multi-layer types. When identifying targets, MLTA resolves each layer and calculates intersection of their target sets. So for the indirect call at line 28, we can see MLTA identifies these two functions as targets, while in fact we know only one of them is a real target. So MLTA produces false positive targets because of the splitting and the intersection operations. To mitigate these false positives and further refine indirect call targets, we propose strong multi-layer type analysis, SMLTA. It keeps strong restrictions provided by multi-layer types by recording mappings between entire multi-layer types and associated functions in a data structure called a type-func map, because it's a mapping from type to func, as this table shows. Then SMLTA resolves the entire multi-layer type of each indirect call, producing the result write to shared mem for the indirect call at line 28, which is exactly the only real target for this indirect call. The prototype of SMLTA is called DEEPTYPE. Here is the workflow. The input is program bitcode. In phase 1, DEEPTYPE collects type information and records the information in 3 different data structures. The first one has just introduced in the previous slide, and the other 2 data structures will be introduced later. In phase 2, DEEPTYPE analyzes indirect calls using the collected information in these 3 data structures and outputs a list of indirect calls for this program, along with their respective target sets. In phase 1, we first resolve the relationships between multiple types to address the challenges caused by type transformation. There are 2 kinds of type transformation. First is type assignment. It assigns a variable with one multiple type to another variable with another multiple type, leading to information flow from the source type to the destination type. Typecasting casts one type to another type, leading to bidirectional information flow between source and the destination types. We propose friend type to describe the relationship. To be specific, a multiple type A is a friend type relative to a multiple type B if there exists information flow from A to B. It is called friend type because A can share its associated functions with B through the information flow. Then the relationships are recorded in the data structure called type map because it records the mapping between multiple types and their friend types. For large programs, we know there are numerous multiple types in it. To better organize them, we propose multiple mapping, and it used to record multiple types in a data structure called type lookup map. This data structure contains multiple maps and the mappings between these maps. Due to time limitation, I will not go into details about this data structure. If you are interested in it, you can find more details in our paper. So in simple word, with this data structure, looking up a multiple type in it just follows the same way as looking up a word in a dictionary, which provides efficient access and retrieval. In phase 2, we propose a conservative approach, a conservative solution called fuzzy type. It is used to address the challenges caused by parameter parsing. Fuzzy type marks the type of uncertain layers. Here, the formal parameter I call PTR has type FP. But we don't know whether this formal parameter has any outer layers that are missed during the process of parameter parsing. So we use fuzzy type to mark the type of the uncertain layers. Fuzzy type can match with any type, allowing FP fuzzy type to match with all here listed multiple types as long as the first layer is FP. In this way, we can ensure that all potential targets can be collected if the formal parameter is used to make an indirect call. To identify targets for indirect calls, we first ascertain its multiple type, then query type map for friend types relative to each fragment because the information flow can happen on fragments. Here, a fragment is one or multiple continuous layers in our multiple type. We use adapted breadth-first search to exhaustively search for all friend types in this program. Then generate friend types for the entire multiple type and look for matched types in type lookup maps. Finally, we query type func map to achieve valid targets. In implementation optimization, we use special handlings to address corner cases, which reduces both false positives and false negatives for precision improvement. We also use caches to store the result of resolved multiple types for efficiency improvement. In evaluation, we evaluated the effectiveness and the efficiency of DEEPTYPE. Here shows the experiment environment and the benchmarks we used in our experiments. DEEPTYPE is compiled with TypeDive, which is a prototype of MLTA. We use a metric, average number of targets, ANT, to quantitatively measure effectiveness. It is a quotient between the total number of targets and the total number of indirect calls with targets. This table shows the ANT value of DEEPTYPE and TypeDive. We can see for most benchmarks, DEEPTYPE reduces the ANT value by 43% on average. This reduction owes to SMLTA and the special handling in optimization. Both of them reduces false positives. For the remaining benchmarks, we can see DEEPTYPE does not consistently reduce ANT, but it does not mean DEEPTYPE is less effective. In contrary, the increased ANT value results from the special handling in our optimization because it can reduce false positives. On the other hand, the implementation issue in TypeDive also produce extra false negatives. So DEEPTYPE is more effective than TypeDive. But how much effectiveness is contributed by SMLTA? This table shows the answer. It shows the ANT value of DEEPTYPE, DT-no-sh, and DT-weak. Here, DT-no-sh is DEEPTYPE without special handling. We can see the ANT values of DEEPTYPE and DT-no-sh are extremely close, showing that the impact of special handling is trivial because it is designed for corner cases. And the extremely close ANT values also reveal the significant impact of SMLTA on effectiveness. DT-weak is a variant of DEEPTYPE. The only difference is that DT-weak stores split types just like what MLTA does. We can see DT-weak has higher ANT values than DEEPTYPE, shows the impact of storing entire modular types in reducing false positives. This figure shows the execution time of DEEPTYPE and TypeDive. Let's look at Linux as an example. DEEPTYPE spent only 65 seconds to analyze Linux, while TypeDive spent almost double time. The similar trend can be observed from the other benchmarks. So overall, DEEPTYPE outperforms TypeDive, showing an average reduction of 37%. So we say DEEPTYPE is more efficient than TypeDive. In conclusion, we introduced the strong modular type analysis, SMLTA, a novel approach in refining indirect call targets. We implemented it in DEEPTYPE, which is scalable to large applications with superior effectiveness as well as performance over TypeDive. Our artifact is open sourced. It is available on GitHub. So if you are interested in our work, maybe you can check our paper, check our artifact for more information. Thank you for listening.